Hello, we would like to present our third phase of data warehousing project. It's dedicated to data warehouse optimization and OLAP analysis. We would like to start from tools we've chosen. Then we would like to describe the creation of lab cubes, the optimization techniques we used. In the end, we will provide examples of our reports. For our third phase of the project, we choose Mondrian and OLAP Server and Pentaho Business Analytics for visual analysis. For creating the cube schemas, we used the Pentaho Schema Workbench. Our choice was dedicated by the need of Unix and Postgres compatible free solutions. In order to recap, we would like to present our last version of the FM model. For creating OLAP cube schemas, we used Mondrian Schema Workbench. Each cube has only one fact table. The procedure of creating a cube is the following. First of all, we have to create schema, then we add a cube, add fact table, create dimensions with hierarchies, and add measures. In this example, you can see a cube for fact song features. According to our DFM model, we have to create dimensions, date with corresponding hierarchy, decade, year, month, geography dimension with continent, country hierarchy, and song dimension. We also added all necessary measures like min, max, average duration, min, max, average loudness, min, max, average tempo, and count. The first and the main problem we had to handle on this stage was the huge amount of many-to-many relations. When we were working on our initial DFM model and did the research on the sources, we wanted our data warehouse to contain as much information as possible. We couldn't allow ourselves to lose any relations between entities, so we ended up with 7 many-to-many relations in our DFM. Many of those are double-leveled, like for example song, which can have many releases at the same time. One release can have many labels. The software we used, namely Mondrian, doesn't handle many-to-many relations, so we had to come up with the way to handle it ourselves. This is what we did. First, we analyzed the measures we have and the aggregate operations we want to perform on them. It turned out that almost all measures we have in our database are aggregated with the help of min, max, average aggregators. This means that is, for example, one song belongs to many releases, and if we perform join of our fact table through song with release, we will end up with one song replicated multiple times but with different releases. But taking into account the nature of our aggregators, the measures average, min, max will stay the same. Situation is different with count. Yes, the count of songs for each release will be correct, but the total count will be wrong. Moreover, joining all our tables would be an explosion in our database, as all the tables are huge. For example, fact song features fact has around 1 million records. After join with release, it's around 4 million records. After join of that one with label, it's already 10 million records. Joining this would affect the performance of our system drastically, so the final solution was to create for each many-to-many relation a separate fact. For example, we have a many-to-many relations between the song and the release. In this particular case, we will have two cubes, one with fact and song, another with fact and release. If we want to count the amount of songs, we use first one. If we want to roll up to release, we use the second one. Here is the example. The first table is records from fact song features. After join with the release, we will have 5 records. So now we have duplicate rows in this table. Counting the amount of songs per release will be correct. 2 songs in release with read number 2, 2 in release number 4 and 1 in release number 1. But using this table to count songs is not correct. The final amount of songs will be 5, while there is only 3. So we use the first fact table for counting the songs and the second one to aggregate on release. Second table we create as a materialized view. We came to this decision because materialized views are pretty much like tables. You can create indexes on those. You can cluster them and so on. In this way we described before, we handle many-to-many relations and created all necessary cubes.
Postgres does not support neither bitmap indexes nor bitmap join indexes. We often mention bitmap indexes where they are applicable, but we couldn't test their performance practically. Suppose we would like to check general statistic about songs produced each year disaggregating by location. Typical query will be like to show average duration of songs of 2009 year in USA. The underlying code of this query is select average duration, year and name from fact tables, year, month, country tables, and group by year and name. The underlying query plan is following. As you might see, execution time of this query is around 2076 milliseconds. The query plan already gives us some insights. Our snowflakes will be joined very often. We should facilitate these joins as much as possible. To avoid sequential scans on huge fact tables, when the part of values to retrieve is relatively small, we should create indexes on the foreign key attributes on the fact table. So optimization strategy is following. Ideal scenario would be a bitmap join index from country and year into fact table. Country has 264 values, year has 162 values. So if we could keep two bitmaps mapping year and country values into fact table, we could perform an operation on these two bitmaps and extract from fact table only those values which correspond to country, like United States and year 2009. In our case, we did following. We created indexes on fact song features on month ID, on country ID and month year ID to facilitate joins. Other indexes that could be considered here are on country name. Hash index as range queries are not expected here. On year, B3 range queries are expected. But we believe this wouldn't influence performance drastically, so country table has only 264 values, year table has 162 values. So here is the result. And execution time is 40 milliseconds. As we can see here, Optimize decided to use the index on month year ID index to join year with month, fact song features MID ID to join the result with the fact table, and finally has joined it with the country table. The gain was around 276%. Another thing we can do to speed up this query and others like this, one is create the clustered index on country ID column in fact song features. This, in our case, will work pretty much like horizontal partitioning on country. So when the queries like where the country is United Kingdom or where country is in United States, Germany, France will be executed, optimizer will read only very small part of the table facts on features, and all the records corresponding to those countries will be grouped together. Another example of query might be show years when label Colombia was produced more than 500 songs. As previously mentioned, to enable analysis by label, we had to handle its many-to-many relation with release and later the many-to-many relations between the releases and song. For this, we created materialized view, facts on label connecting facts on features, fact and labels. The underlying query is, and the initial query execution plan is the following. Execution time is around 1000 milliseconds. As we already said, we need to facilitate joins between the fact table and the dimension table. As we earlier said, that Postgres does not support bitmap indexes, but it has another interesting technique, bitmap heap scan. A plain index scan fetches one tuple pointer at a time from the index and immediately visits that tuple into a table. A bitmap scan fetches all the tuple pointers from the index in one go, sort them using in-memory bitmap data structure, and then visit the table tuples in physical tuple location order. The bitmap scan improves locality of reference to the table at the cost of more bookkeeping overhead to manage the bitmap data structure, and at the cost that data is not longer retrieved in the index order, which doesn't matter for your query but would matter if you set order by. If the bitmap gets too large, we convert it to loosey style, in which we only remember which page contains matching tuples instead of remembering each tuple individually. When that happens, the table vision phase has to examine each tuple on the page and recheck the scan condition to see which tuples to return. So we decided to take use of it. We expect many queries with grouping by label, label city, label country, label continent. It would be great if the fact records corresponding to one label, those fact records corresponding to labels of one country, and so on, were all grouped together. That is why, when creating our materialized view, we grouped the fact records first by continent, then by country, then by city, then by label. Now we have to add index on the fact table label ID. We see the change in our query plan. Now the first thing Optimize does is use bitmap scan on fact song label table. To find the fact records of label Columbia, it scans the index, creates the bitmap structure, sorts it, and then visits the pages when have the needed records. In our case, as our fact table is grouped by labels, the number of such pages is minimal. Unfortunately, there is no way to tell the optimizer about this custom clustering. That's why, when it will estimate that the number of records to retrieve is huge, it will most probably prefer the sequential scan in the fact table to the use of index. Other indexes we are added to facilitate these queries are following: index on label, we expect many filtering on labels, and index on fact, country ID, fact, month ID, for obvious reasons. Speedup was around 50%.
Another example of the query is to show the number of songs by studio by decade. The underlying query for this and the initial query execution plan you can see on the slide. Here we need to join 4 tables fully, so indexes cannot facilitate this join, but probably during the analysis process queries will be more localized. By this we mean cube slicing. The indexes might become handy, so we create them anyway. The next example of the query is to show the number of songs of genre pop grouped by year. The queries that do the selection on genre, which are very probable in our data warehouse, can benefit from creating clustered index on genre ID field of our fact table. As we can see, the execution time is around 762 milliseconds. So we created index on genre ID field and we clustered it. Now, after clustering, the use of Postgres bitmap heap scan is extremely effective, as all facts corresponding to one genre are now grouped together, so the amount of input-outputs optimizer needs to do to read records of pop genre is minimum. So the speed up is around 56%. So during the optimization stage, we analyzed the most frequent query types in our workload. We created indexes to facilitate the most frequent joins. We created materialized views to avoid joining huge table in many-to-many relations. We created clustered indexes to take the most out of Postgres bitmap heap scan.
Now I would like to show you the reporting tool we chose to work with. Let's create one of the reports so that you can see how to work with it. We create a new analysis report. Let's choose one of our fact tables here. And here we go. Here are some measures we can use for our analysis. Here are some hierarchies, and we can put filters here. And here the result will be displayed. Let's, for example, count the number of songs of our favorite artists by year. Let's first choose the artists. Filter out. We want to know information on Arctic monkeys. Maroon 5. And the Killers. Here we go. Now we should include artists into one of the levels of our table. Let's put artists on the columns. On the rows, let's put the year. But let's first filter out the unknown year, because we want only those which are known. In our case, it's denoted as 0. It's excluded. And here we go. Now we put year on the rows of our table. Now we should choose the measure. Let's choose the distinct count of songs these artists produced by year. Here are the results, but they're not representative, of course. So let's choose the visual representation of our results. I believe the line diagram should work the best. So here we see that the Killers were more productive in 2004 and Arctic monkeys were more productive in 2007, and well, we believe this is a very representative graph. Now let's see how popular are our favorite artists in different countries. For this we have information about song plays. Let's create another report. Let's choose one of our fact tables. Again, we want to filter out only the artists we want to know info about. The same artists. We can put them on one of the levels. Here. We want to know the number of plays, but let's be more specific. Let's choose users from English-speaking countries. So here we choose that we want to know statistics from users of United States, United Kingdom, Australia, and Canada. We obviously don't have any listening statistics about the Killers, but let's see about these two. Let's put the user country on the rows of our table, and now we can select the measure someplace. Here we see, but again we want something more representative, so let's go into visual analytics. We have statistics about all 4 countries, but it would be great if we switched them. It would be more representative. Yeah, here we go. Well, we can see some interesting statistics here. We see that Arctic monkeys are much more popular than Maroon 5, which is obvious. And Arctic monkeys are much more listened to in United Kingdom, their home country, than in United States, for example. While Maroon 5 are much more listened to in United States, which is their home country, which is kind of interesting statistics. But let's see like this, because now we can see the difference. Well, the share of Maroon 5 in United States is around 57% of all these, while of Arctic Monkeys it's only 33%. Well, this was pretty interesting analytics we consider. Our final report will be about the genre evolution. Let's create a new report. We want to see information about some very popular genres. Let's choose rock. Normal one. Pop. And for example, jazz. And classical music. Good. Let's put genre on columns. We want to know information on decades because it will be more representative. Again, let's exclude unknown decade and put decades on our rows. We want to know average hotness of these songs. Well, here's our result. Again, we want to see something more representative. Well, here we go. We can see some interesting tendencies here. For example, that in 90s classical was much more popular and hot than all the rock and pops, which were the favorites all the previous years. And we can see, for example, then in 60s rock was more popular than pop, while now pop is more popular than rock, and some other interesting tendencies. Well, we don't have much information before the 1950s, but still, it's very interesting. So these are all reports we wanted to show you. As we mentioned earlier, we can divide all our queries in 3 categories. The first category is statistics about songs and artists. The second one is statistics about song musical features. And the last one is analysis of user ratings and user behavior. We can use 3 data marts for these purposes. The first one will be useful for regular users, the second one for musicians and professionals in music industry, and the last one will be useful for marketing analysts. For drawing information for different types of user from data marts, we will use created OLAP cubes. For example, marketing analysts can be interested in the number of plays by song and year and location, and we can get all this information from our created cube song play statistics. Number of songs by features like key, tempo, duration, mode, disaggregating by genre or artist can be interesting for professionals in music industry. And we can find all necessary information using cube about song features.
Here is our Gantt chart. Thanks for attention.